For decades, our collective dream of the future has looked exactly like this. Red dust, pressurized domes, a struggle for survival on the surface of Mars. We assume that because we evolved on a planet, our destiny lies on another one. It is what Carl Sagan once called planetary chauvinism. But what if the best real estate in the solar system isn't on a planet at all? What if we could build a world that is mathematically perfect? A place with Earth-normal gravity, 24-hour sunlight control, and a total surface area capable of accommodating several million people, constructed entirely from materials we already know how to mine. This isn't science fiction, it's a solution proposed by a Princeton physicist over 50 years ago, a solution we ignored in favor of the romance of Mars. But as we face the limitations of rocketry and the fragility of our own biosphere, we are beginning to realize that he may have been right all along. Why do we need to find a second Earth when we can build one instead? I'm Max Anderson, and you're watching Quantum Reach. Today, we're investigating why the future of humanity might not be under an alien sky, but inside a spinning metal tube. To understand why we would go to the immense trouble of building a continent in the stars, we first have to look at the problem with planets. In September 1974, Dr. Gerard O'Neill published a landmark paper in Physics Today. O'Neill asked a simple question to his physics students. Is the surface of a planet really the right place for an expanding technological civilization? The answer, surprisingly, is no. Planets are gravity traps. They are energetically expensive to leave and difficult to land on. Furthermore, they come with unchangeable settings. Mars has a gravity roughly 38% of Earth's. It's doubtful a human child could even grow up healthily in that environment. As O'Neill himself put it, a point often missed is that for the first time we can have the conditions of the surface of the Earth anywhere in the solar system. O'Neill realized that if you want to create a habitat for millions of people, you don't hunt for a rock that is good enough. You take the raw materials and arrange them into the most efficient shape possible. And by O'Neill's calculations, he showed that for a massive, self-contained and controllable world, the most logical shape isn't a solid sphere, it's a pressurized, rotating cylinder. So, let's break this down. O'Neill's classic Island 3 design consists of two cylinders, each 20 miles long and 4 miles in diameter, rotating in opposite directions. Why two, you might ask? A single massive rotating object in space would drift, pulled by its own angular momentum. That's gyroscopic instability. But two cylinders rotating in opposite directions cancel each other's gyroscopic effects, remaining orientated towards the sun and maintaining stable operations. The pair would orbit around a common center of mass, a barycenter point in the empty space between them. Not so different from how Earth and the Moon dance around each other, just on a much smaller scale. And that has implications. These wouldn't be isolated structures, but naturally paired communities, twin cities in space, each with potentially different environments, cultures, and economies. Humanity diversifying across multiple worlds, all within a short shuttle ride's distance of each other. But the real magic happens inside. To replicate Earth, you need Earth's gravity. In space, we fake it with rotation. The cylinder rotates roughly 40 times per hour. That's once every 90 seconds. Of course, this depends on the diameter of our cylinder. If you are standing on the interior surface, the centrifugal force pushes you against the hull, simulating gravity perfectly. Now, you might be thinking, wouldn't I get dizzy spinning that fast? And that is a valid concern. If the radius is too small, the difference in force between your head and your feet would make you nauseous every time you stood up. But because O'Neill's design is 4 miles wide, the curve is so gradual that your inner ear wouldn't notice the rotation at all. You could pour a cup of coffee, play a game of catch, or walk a tightrope, and it would feel exactly like standing in a park in London or New York. However, gravity is only half the equation. Life requires energy. On Earth, we are at the mercy of the weather. On Mars, you are twice as far from the Sun, but an O'Neill cylinder is designed to be in a constant, unblinking bath of solar radiation. The cylinder walls are divided into 6 strips. 3 are land areas, and 3 are windows. Floating outside are 3 massive, movable mirrors. These reflect sunlight through the window and onto the land strips opposite them. This gives you complete control of the day and night cycle. Want a 24-hour day? Done. Want to simulate winter to help your apple trees blossom? We can just tilt the mirrors. You effectively separate the light from the heat. You get the visual beauty of the sun without the cosmic radiation. It's a climate-controlled Eden. Take a walk toward the cylinder's central axes, and gravity decreases. Not suddenly, but gradually, like wading into deeper water and feeling your weight slip away. At the central axis, we have zero gravity, which becomes a natural recreation zone for the cylinder. Imagine swimming through the air, playing sports that can't exist on any planet, and watching aerial dances where movement feels more like flowing through water than falling. But here is where things become challenging. An O'Neill cylinder needs roughly 1 billion tons of material: steel, aluminium, titanium, and silicon for its windows. At today's launch costs of around $2,600 per kilogram, that's an astounding $2.6 quadrillion just to get the materials off of Earth. Dr. O'Neill realized we don't need to bring the material up from Earth at all. The moon's surface, also known as regolith, is rich in aluminium, titanium, and silicon, the exact ingredients needed to build these habitats. O'Neill proposed a mass driver, essentially a long electromagnetic railgun, that could accelerate packets of lunar soil to escape velocity, flinging them to a stable point in space called a Lagrange point, specifically the L5 point of our solar system. Objects could remain here indefinitely. It's like a cosmic parking lot. Once the material arrives, we can refine it in zero-gravity smelters using endless solar power. Then we print the colony in space. No launch costs and no pollution on Earth. Later, as we expand, asteroid mining becomes a lucrative source of metals. A single metallic asteroid contains more platinum, cobalt, and rare metals than humanity has extracted from the Earth in its entire history. If we can pull this off, and the physics says we can, the implications are staggering. A single O'Neill cylinder could house several million people, but we wouldn't stop at one. With the material from the asteroid belt alone, we could build enough cylinders to create a land area 3,000 times the surface of the Earth. Just think about that. As O'Neill wrote in The High Frontier, the surface area in the colonies is not limited to the surface area of a single planet or moon. As in, we could house trillions of humans, each with acres of living space, without ever colonizing a planet. This changes the very nature of civilization. On a planet, you are separated by oceans and borders. In a cylinder cluster, you are separated by a short shuttle ride. But perhaps the most profound realization is what this does for Earth. O'Neill viewed Earth not as a place to be exploited, but as a park to be preserved. By moving heavy industry and the growing population into space, we allow the Earth to heal. We stop digging up our home to build our future. Instead, we use the dead rocks of the solar system to build gardens in the sky. The dream of Mars is romantic. It appeals to the explorer in us who wants to stand on a new horizon. But the O'Neill cylinder appeals to the builder in us. We must, however, be honest about the timeline. We are not going to build Island 3 tomorrow. We need to return to the moon first. We need to master asteroid mining. And we need to build the infrastructure that builds the infrastructure. So, when does this all happen? Let's take a look at one potential timeline. 2050s through to the 2070s, we could call this the foundation phase. We establish permanent lunar mining infrastructure with in-space refining and manufacturing capabilities. Small rotating habitats for testing, maybe 1 kilometer in diameter, housing possibly only thousands. At this stage of development, we are still learning from our mistakes, while the stakes are low. As we move to the 2080s and through to the 2120s, we would see larger prototype cylinders being constructed. At this stage, we could possibly see Island 1 and Island 2 designs come online. These would be smaller O'Neill-style habitats, perhaps 5 to 10 kilometers long, with populations in the tens of thousands. This gives us a chance to perfect the technology and prove it works at scale. Moving towards the 2200s, it's possible that we'd see full-scale construction of Island 3, the complete O'Neill cylinder, with advanced robotics and autonomous manufacturing. Estimates put the construction time at around 20 to 40 years. Recent engineering studies suggest a smaller O'Neill cylinder could cost as little as $200 billion, roughly 2 years of NASA's current budget. The assumptions are that reusable rockets like SpaceX's Starship could drop launch costs to as low as $200 per kilogram, that lunar mining is operational, and that construction can largely be completed by a robotic workforce. To put that in perspective, the US interstate highway system cost $500 billion as of 2016, and the International Space Station, housing only up to a dozen people, cost $150 billion. An O'Neill cylinder housing thousands? Sure, it's ambitious. Challenging? Absolutely. But science fiction? Perhaps not. So, what's life actually like inside of our cylinder? You wake up to a beautiful sunrise as the gigantic mirrors slowly bloom open, letting natural light spill across the curving landscape. You step onto your balcony and take in the city around you. Below, a river threads its way through parks and forests, while above, a whole nother city floats across the sky, its buildings rising downwards like a reflection in some impossible mirror, perfectly ordinary to the people who call it home. Your commute takes place in a small electric aircraft. It lifts off smoothly, climbing through the bands of steadily weakening gravity as the cylinder's rotation affects you less and less. By the time you reach the center axis, you're almost weightless, drifting in your seat while the craft glides along its route before beginning its slow descent towards the far side. Gravity gradually returns as it approaches the outer surface again. The entire trip takes about 10 minutes, no traffic, no delays, just a quiet hop across the interior world. Your afternoon might take you to one of the microgravity labs near the hub, where perfect crystals for quantum processors grow without distortion. Others work on pharmaceuticals that can only be synthesized in weightlessness, or on precision-engineered components destined for the next cylinder under construction just a short hop away. Evenings in the cylinder are full of rest and relaxation. Amphitheaters are built directly into the sloping terrain, their seating curving with the landscape, while restaurants stretch along the interior horizon so that you can look across the center and see diners on the opposite side, tiny figures against the distant art of the cylinder's interior surface. When you look towards the long window strips, there's no sky in the earthly sense, only open space, with Earth and the Moon slowly drifting past as the cylinder completes its steady rotation. At night, the artificial lighting system lowers itself to a soft glow as the mirrors retract, and the gardens along the walkways come alive with engineered bioluminescent plants that outline footpaths in shifting blues and greens. Families gather near the viewing windows where the stars are sharp and unobstructed. Children point excitedly at the faint red glimmer of Mars. Out there, other cylinders orbit in distant lanes, forming a chain of habitats, humanity growing outward, not by settling harsh planetary surfaces, but by constructing entire worlds suited to its needs. We know that the physics works, and the blueprint has been waiting for us since 1974. The question isn't whether we can do it. The question is whether we are willing to look past the planets and realize that the best world for humanity might be the one we build for ourselves. The O'Neill cylinder represents more than engineering. It's a philosophical shift in our exploration of the universe. For a century, we've imagined space colonization means enduring hostile surfaces, low gravity, radiation, and toxic soil. Planets come with fixed conditions to which we would have to adapt to survive. O'Neill cylinders offer something different. Worlds designed for us by us. And unlike planets, you can build thousands of them. By the year 2300, we might not have cities on Mars. Instead, we might have thousands of cylinders, each its own unique environment, housing millions, forming an interplanetary civilization more diverse and resilient than Earth ever was. Some cylinders might simulate Earth's biomes, rainforests, grasslands, oceans. Others could be optimized for industry, research, or agriculture. Still others might be entirely novel environments, ecosystems built for leisure that never existed on any planet. We're expanding what it means to be human beyond a single planet's surface. We have become the builders of worlds. The question isn't whether we can build these, physics works, and the engineering is understood. The question is when we decide we're ready to become something more than a single planet species. When are we ready to build our own paradise among the stars? What do you think? Would you choose a dusty dome hiding from the solar radiation on Mars, or a beautiful garden in a climate-controlled cylinder floating amongst the stars? Let me know your thoughts in the comments below. Thanks for watching. This is Quantum Reach. Goodbye.